classical mechanics, there is an abundance of work done with pendulums in regards to two-dimensional space. The experiment and mathematical research we performed will help us see how pendulums work in the real world, which we all know is three-dimensional. An interesting component to this experiment is observing the rotation that is being done on the pendulum as it swings. Many amusement parks all over the world have some type of ride or attraction with some sort of rotating body swinging freely. For example, the Windseeker at Cedar Point and Kings Island in Ohio is the best real-world example of what is trying to be shown in this experiment, which is the motion of pendulums at the swings while rotating about a fixed vertical axis. The goal of this project is to try to predict and map out the motion of such rides with the help of a pendulum without using non-inertial frames, as well as to see if it is possible to calculate the centripetal acceleration, time, period, and frequency of the system. We want to do this by analyzing the motion of the pendulum attached to a rotating body, as it's also preferable to analyze the kinematics of the system too. For this topic, we will use basic knowledge of pendulums in regards to Lagrangian mechanics, energy, and circular motion.
The construction for this experiment starts with a bike wheel and a pendulum, which in this case is a keychain that has been attached to the bike wheel, and a sturdy base. What we did is we took an electrical box that you can find at Home Depot or Lowe's, and this is a piece of metal conduit with a clamp on the end that has a screw on one end to clamp onto the metal conduit and threaded on the other end. The threaded piece goes through into the electrical box, and there's actually, as you can see here, a little washer that goes underneath. This is just for the purpose of explaining. This will screw in here, and the washer will keep it tight on the bottom. And then up on top, there's this clamp. This has the same screw, but in this case, this clamp goes onto this nut, just like that. And then once it's on, you're able to screw in the clamp to tighten it on top, and then the bike wheel will be able to spin freely once it's tight. For our experiment, our constants were the height of the wheel, which was 74 centimeters, the radius of the wheel, which is 20 centimeters, the length of the string at 17.5 centimeters, and the mass of the object, which was 12 grams. Several video cameras were used to give us better angles and to keep our data more precise. The videos gave us the ability to take screenshots at specific times and then use those screenshots in an application to find the angles that were created at certain points in rotation. With the videos, it was possible to calculate the time period, the frequency, and the angular velocity. For the first part of the experiment, we were able to use Newton's second law to get an equation of the centripetal acceleration in terms of the gravity and the angle moved in the x direction. We were then able to manipulate the formula for centripetal acceleration to get an equation for time period. This equation can also be manipulated to give radius when the time period is known. The calculated time periods were then compared with the experimental time periods. The results were very similar, with the maximum difference being 0.22 seconds and the minimum being 0.06 seconds. Some causes for this discrepancy would be air resistance and friction. For the next part of the experiment, we needed to make sure the equations of motion derived were correct even though the math was not done in non-inertial frames. So the coordinate system was set up in a way that the rotation of the wheel was also being considered. To make the math easier to go through, we first calculated the time derivatives and then put the values in the formula of kinetic energy and potential energy.
In regards to COVID-19, it was not attempted, unfortunately. With that being said, the results received from the equation of motions are the same as the results from before. So for this scenario, the equations of motions of the systems can be done without using non-inertial frames.
While the derivations done to get the equation are very long and a bit confusing at times, the end product came out to be pretty neat. Unfortunately, due to the time limitations in the current situation, we are not able to test or map out these equations, and so we cannot be completely sure it is accurate. However, we were able to find a paper similar to ours in which they derive the equation of motions of a pendulum which is attached to a rotating amusement park ride. The coordinate system did not account for the rotation of the ride, as They considered the inertial frame and fictitious force in their calculations. However, when the same arbitrary values were put in our equations, the theta and phi double dot were equal or very close to theirs. This, while not being an accurate test, gives us some legitimacy for our equations.
Through our experiment and research, we were able to successfully calculate the centripetal acceleration, time period, and frequency. The values calculated compared to the values found from the experiment were all relatively close to each other as well. Aside from actual values versus calculated values, our main source of errors came from the video camera and screenshots, since it wasn't very easy to get screenshots taken at the exact same moment on each video. We got our angles close, but not perfect. The Lagrangian gave an equation of motion for the pendulum, however, it is not analytically solvable. These equations are numerically solvable, however, but due to time constraints and the current situation in regards to COVID-19, it was not attempted, unfortunately. With that being said, the results received from the equation of motions are the same as the results from before. So for this scenario, the equations of motions of the systems can be done without using non-inertial frames.